So now let's review something we had looked at before. We had started a lecture off talking about that images best represented in this coordinate frame x and y, but an object in the real world, and I referred to them as capital X, Y, and Z, with Z is in the inside the camera lens itself. That is the depth. Y and X basically showed the width and the height of an object. So if I had an object like this, I actually would capture an image in, of course, the coordinate frame x and y here. We represented that scene in 3D this way, where now basically I've turned it around. Z is going in this direction, Y and X are this way. And of course the same object is here, shown by this arrow. And here I'm just giving it, values of X, O, Y, O, and Z, O in capitals. Let's build this to kind of see what the camera model would look like and how we can compute depth. These are the coordinate frames in real world coordinates. Of course, in a camera, an image is formed. Here I basically show this image and the coordinates x and y sub I for image. Of course, this image is being formed at focal length f. And if you remember, when we looked at cameras, we did all of the calculations, that is the similar triangles, to figure out that xi over f is equal to x0 z0 because focal length is this distance and these are two similar triangles. And of course I want to be able to use this to compute where the x would be in the image, and this would be my equation. Similarly for y sub I, that is the pixel information in this image, is basically related to both the focal length, how far it is, and knowing information like where the z is, how far away this object is from the scene. Notice this information is not contained in this image. That is, where is z? And that's the point that we want to actually now start thinking about how to compute. So in essence, this equation would apply the same if this point was here. So this point here could actually be at this location. Same equations would apply. Also, if I can basically find any point in this line here, which is the ray of light that's going through this point. So the point I wanted to emphasize here is there is a fundamental ambiguity here. That is, any point on this line in the same ray maps to the same point on the image plane, right? Any point here, of course, the values of z's are different, the values of x and y are different, but when it comes down to where they are, that is x sub I and y sub I, all of those values of any point in this ray of light is going to project exactly to this point. So in essence, what that suggests is I can actually scale any of these three values, x naught, y naught, or z naught, for the world coordinates. Basically, that means put the same scale. This is the same equation. So in essence, that suggests is there is a scaling factor here between both of these images that will actually produce the same xi, yi. And actually, it makes sense, right? As I move closer, the object is getting smaller, and therefore this would be the scaling factor. So moving farther and closer would be the scaling factor, and of course by multiplying and dividing by the same k, we can see that impact. So this is the ambiguity. This is the one we want to resolve in a variety of different ways, and that resolution of that ambiguity will give us depth or structure of a scene.